Okay, this is a big one. Throughout the history of our species, we've discovered 6,000 exoplanets, which are planets outside of our solar system, and out of all of those 6,000, this is the best picture we have ever taken of one. A single blurry dot. Now, I don't know about you, but I want to see rivers, mountains, and maybe even alien cities. But there's a problem. This is JWST, the most powerful telescope ever launched into space, with a mirror 6.5 meters wide. But to take a high-resolution image of an alien planet, we would need a mirror 90 kilometers wide. Okay, so how do we do it? Well, scientists have been quietly working on a solution for nearly a century, dating all the way back to Einstein. There's a way we can turn our sun into a telescope and take a high-resolution picture of an alien world, seeing rivers, continents, and maybe even city lights. I spoke with NASA's lead researcher developing this mission and spent the last year simulating the whole thing. If they pull it off, this could be the single greatest achievement in all of human history. We could be looking at alien cities in your lifetime. In 1992, astronomers found the very first exoplanet, kicking off the exoplanet revolution. They were detecting them in basically two ways. You could either watch a star and wait to see it wiggle a little bit thanks to the planet's gravity, or you could wait for a dip in the star's brightness caused by a planet crossing in front of it, just like the moon dimming the sun during an eclipse. But both of these are indirect methods of finding exoplanets. You look for the effects instead of just pointing a telescope at them and snapping a picture. And so they tried to do exactly that. By the early 2000s, there was some success, but the planets only appeared as tiny little dots, and those tiny dots were huge gas giant planets like Jupiter. Even the best telescopes at the time, like Hubble and huge ground-based observatories, would have no hope of imaging an Earth 2.0, because those planets are just too small and faint. You can do it in theory, but it would take a telescope 2,300 times bigger than any telescope we have ever made. And even if we built a telescope big enough, there's an even worse problem. The host star is simply just too bright. An Earth-like planet is roughly 10 billion times fainter than the star that it orbits. It's literally like trying to take a picture of a firefly beside a huge stadium floodlight from hundreds of miles away. We do have instruments called coronagraphs that physically block the starlight, revealing the planets behind it, but they can only suppress the glare by a factor of about 1 million, and we need 10 billion. That's still 10,000 times too weak. This is known as the contrast problem. So what if we took a completely different approach? In 1915, Albert Einstein published his now famous theory of general relativity, in which gravity is described not as a force pulling on objects, but as the warping of space-time itself. Massive objects like the sun warp the fabric of space-time, and light follows that curvature, bending along with it. Okay, so here's what happens. 20 years after Einstein publishes his theory, a Czech immigrant named Rudy Mandl, who is working as a dishwasher in Washington, D.C., figures out that gravity could magnify starlight like a lens. He went to Princeton to go and meet Einstein and tell him about his idea, but Einstein was dismissive. He said the effect would simply never be observed. But Mandl was persistent. After months of following up, Einstein finally and somewhat reluctantly published a paper detailing this concept. When Einstein finally agreed and sent this paper off to the journal editor, he wrote, "Thank you for your cooperation with the little publication, which Mr. Mandl squeezed out of me. It is of little value, but it makes the poor guy happy." He even ended the paper by writing, "Of course, there is no hope of observing this phenomenon directly." But get this, he was wrong. Decades later, after Einstein's passing, astronomers started seeing his lensing effect everywhere. Distant galaxies being warped and magnified by the gravity of massive objects between us and them. It was creating these beautiful rings of light that are now known as Einstein rings. And then in 1979, a scientist named von R. Eshelman asked a question that changed everything.
And von Eshelman suggested that we can use a gravitational lens, a solar gravitational lens, to communicate with with aliens.
The idea was beautiful, but the technology that it required seemed like something out of science fiction. But today, that might no longer be the case. Here's how it works. Light from the distant exoplanet flies through space and gets ever so slightly deflected by the sun's gravity. because the sun is a sphere. Rays passing on opposite sides bend by the same amount and eventually meet up again along the focal line. That line starts at about 550 AU, where 1 AU is just the distance from the sun to the Earth, and it extends out to infinity. Once you reach that 550 AU mark, the sun would look like this: a bright sphere of light surrounded by a gravitational lens. The picture of the exoplanet that we are targeting is hidden inside that ring. The sun acts like a huge cosmic funnel, gathering photons that left the planet in all different directions and focusing them down to a single point along the focal line. In the wavelengths of light that our eyes can see, this amplifies the brightness by a factor of 100 billion. That is the equivalent of having a telescope with a 90-kilometer wide mirror. So the goal is pick the planet that you want to image, find the line directly opposite the planet behind the sun, send a telescope out along that line and take a picture of the Einstein ring. And remember the contrast problem from earlier, where the host star is just too bright to block out. This method completely avoids it because we're not looking at the star at all. We are focusing directly on the planet's own light. You still have to block out the light from our own sun, but our coronagraphs are already more than powerful enough to do that. And the beautiful part is, because the focal line extends to infinity, the telescope doesn't have to slow down. It can just fly along the line, constantly taking images, and the further it gets, the cleaner the images become, because the contamination from the sun's atmosphere gets weaker. This is the Solar Gravitational Lens Telescope, or SGLT. So let's do it. Let's send a telescope out along the focal line. But first, there's a problem. How do we actually get a telescope out to that distance? 550 AU is farther than anything we have ever sent from the Earth. Okay, just before we take a picture of the exoplanets, I need to take a moment to thank the sponsor of this video, Odoo. If you don't know by now, Odoo is an all-in-one business management software that gives creators and entrepreneurs tools to simplify their day-to-day management. They have 45 easy-to-use applications designed specifically to meet your business needs. Whether you need systems to handle invoicing, accounting, and sales, or even full website creation, hosting, and inventory tracking, Odoo has everything you need. And it's all centralized. You have one single platform running your business. All of your data is stored and maintained seamlessly. My personal favorite part is this makes it really scalable. As your business or your team grows, you can add new tools easily and the system grows with your business. And the best part is, your first app with Odoo is completely free for life with unlimited hosting and support. They will even throw in a free domain for an entire year. So just click the link at the top of the description to check Odoo out. Now let's go take a picture of this alien world. The minimum focal distance of the sun is right here, 547.6 AU. That's 82.3 billion kilometers. It takes light itself over 3 days to cross that distance. Out here, the telescope would be in the space between stars, the interstellar medium. Voyager 1, which was launched in 1977, has traveled 169 AU so far. It's the farthest human-made object. To reach the focal line for SGLT, we need to go 3.3 times farther. And I don't want to be sitting around waiting for 150 years. Chemical propulsion, the kind that powers every rocket launch you have ever seen, maxes out at about 5 AU per year. That's 110 years to reach the focal line. We don't have that time. The best science gets done when people live to see their result. A 150-year timeline doesn't motivate anyone.
I'd like to develop a mission that we can fly within a lifetime of a scientist, but that means we need to fly fast.
So the goal is to have SGLT operational within 25 years. So how do we do that? Well, we need to go fast. After years of testing different possibilities and weighing up solutions, the team has arrived at one favored method: solar sails. Photons of light from the sun don't have any mass, but they do have momentum. This means when they bounce off a highly reflective surface, they give it a little nudge. It's literally like using a sail and wind to cross the ocean, but instead you're using light to cross the cosmos. To hit speeds of 25 AU per year, they need to perform something called the Sundiver Maneuver. You essentially launch the spacecraft on a trajectory towards the sun, the entire thing weighing less than 100 kilograms. and then on the way you will unfurl the solar sail. The design has a central truss extending out either side of the spacecraft, and along it there are 16 rectangular sails, each one with 1,000 square meters of surface area. If you add up all of their surface area, you have about 2.5 football fields worth of sail. And it is designed like this so each sail can independently tilt, allowing the spacecraft to be accurately steered. Here's where it gets crazy. The sail needs to be unbelievably thin, about 70 times thinner than a single human hair. That entire huge sail weighs only 32 kilograms since it's made of an extremely light tin-coated carbon nanotube film. They are going to be so close to the sun that the sail needs to be able to survive at 3,200 degrees Celsius. That's 2 times hotter than the melting point of steel. As they get close to the sun, the sails will be angled perpendicular to the star, meaning they won't get pushed off course. And then at their closest point, they will be just 15 million kilometers from the sun's surface, about 1/10 of the distance from the Earth to the sun. Getting close gives them a huge gravity assist, the sun's gravity whipping the spacecraft around and throwing it out of the solar system on the required trajectory for the focal line. At that closest approach, the solar sails will then snap into place, allowing the sun's light to rapidly accelerate the spacecraft. The Sundiver Maneuver gets them up to 125 kilometers per second, about 26 AU per year. At that speed, they will reach the focal line in just 20 years. After 2 years, the sails are no longer of any use since the sunlight is just too weak at the outer edges of the solar system, so they get ejected off into space. After 7 years, the spacecraft passes Voyager 1, and then finally, after the full 20 years, the telescope is in place along the focal line, and it will begin operations for the next 10 years. Now picture this. We build the telescope and we send it out there and wait 20 years, and then finally we turn it on and the telescope is broken. What do we do? Well, of course, the SGLT team have thought of this too. So the plan isn't just to send one spacecraft, but hundreds. Here's how it works. Each launch carries 6 CubeSats, and each one has a specific job. Some carry mirror segments for the telescope. One carries a coronagraph to block out the sun. One handles communications back to the Earth. And one carries nuclear power because out where they're going, there's not enough sunlight for solar panels to work. Each of these little CubeSats has their own solar sail to launch them on the right trajectory, and once they're ejected, they can then be autonomously assembled into a mission-ready spacecraft. The telescope itself doesn't need to be huge, only about a 1-meter mirror. This is because the sun does all of the hard work for you. You just need to be out there to capture the image. And they won't just take one of these. You need 5 or 6 of these mission-ready spacecraft to take the image, since getting a picture of a planet out of that Einstein ring can be a little tricky. And here's the craziest part. They want to launch a full group of these spacecraft every single year. This forms what they are calling the string of pearls. It's kind of like a necklace stretching from the sun out into interstellar space. Each pearl is a cluster of tiny spacecraft launched a year apart. This spaces them 25 AU from each other. That's about the distance from the sun to Neptune. And I love this because it means if something goes wrong with one of the pearls or one of the telescopes, the mission is okay. The pearls will use laser communications to beam their data from one pearl to the next, eventually chaining it back to the Earth. The entire image will only be about 6 megabytes and take around 13 hours to transmit, minus the light travel time, of course. Each pearl has enough hardware to form a full imaging system with all of the telescopes, power, and communication. Together they form a relay chain, a fleet of observatories, and a full backup system all in one. The later pearls get to incorporate newer and better tech. A pearl launched in year 5 benefits from 5 more years of material science, computing, and AI. Okay, there's one thing I haven't told you about this mission yet. There isn't just one focal line. There's infinite. Every planet has its very own focal line on the direct opposite side of the sun. This means we won't just be targeting a single planet. We will instead pick a number of different targets, each one with their own focal line. The team has a short list of candidates like Kepler 186f, the first Earth-sized planet found in a habitable zone, and LHS 1140b, the eyeball planet. But here are the top 3 targets. Number 3 is GJ273b, a super Earth located 12.4 light years away from us. This world orbits an extremely quiet red dwarf star and receives just 6% more light from its star than Earth. It is one of the best candidates for habitability among known exoplanets. Number 2 is the famous TRAPPIST-1 system, and this one is special. It's located 40.7 light years away, and it contains 3 rocky worlds, either inside or really close to the habitable zone. This gives the team a unique chance to image multiple planets from a single star system. And number 1 is Proxima Centauri b, our nearest neighbor, just 4.24 light years away, the closest known potentially habitable exoplanet. This means we will have the greatest surface level resolution when imaging this planet. If there are aliens living there, we should be able to see them with SGLT. With these targets, this is what our mission looks like. Focal lines extending out into interstellar space. Each one gets its own array of spacecraft built to image the Einstein ring and send that data back to the Earth. Okay, so that's the overview of the mission, but once the telescopes are actually out there and traveling along the focal line, how do we actually get an image of a planet out of that Einstein ring? This is where the mission becomes pure genius, and it sounds like science fiction, but this is real physics. This is the focal line for Proxima Centauri b. Let's look at one of our beads. There are 5 1-meter telescopes per bead, and each one of them serve an important purpose. We need to turn this warped Einstein ring into a beautiful image of the planet's surface. The image of the entire planet isn't hidden inside this one ring. It's actually projected out onto the sky as a big cylinder. So we need to move the telescopes along this circle, taking pictures of the Einstein ring at each location. For Proxima Centauri b, the cylinder will be 32 kilometers wide when the telescopes are at 650 AU. As they get further away, the cylinder expands linearly. By the time they are at 1200 AU, the cylinders will be 57 kilometers wide. All of the telescopes are equipped with their own internal coronagraph to block out the bright sun, but there's still a lot of noise coming from the sun's active corona.
And when you buy a telescope, they tell you don't point at the sun. But this is exactly what we have to do.
So to deal with this, 4 of the telescopes will be responsible for imaging the Einstein ring, while one of them sits outside of the imaging cylinder just capturing the sun's corona. This means they will have a clean measure of the sun's atmosphere without the Einstein ring that can then be digitally subtracted from the other 4 telescopes, giving us the clean image of the ring. So here's what they do. They turn that imaging cylinder into a grid, and each square corresponds to 1 pixel in the final image of the planet. For Proxima Centauri b being imaged at 650 AU, each pixel is physically separated by just 31 meters. The 4 telescopes do this dance, moving in a pattern through the grid, taking images of the Einstein ring. But to get a clear picture of the ring that can actually be used to recover the image of the planet, you need to be extremely precise with how you position the telescope. If the position is off by even 1 meter when you take the image, it won't work. Each telescope moves into place, spends 30 to 60 seconds imaging the Einstein ring. The corona measurement from the reference telescope gets subtracted, and you have a clean picture of the ring, where most of the light is coming from the planet itself. You just got 1 pixel. And then they move on, working their way through the grid, but as they get farther from the center, the ring starts to change shape because the sun is slightly oblate. It's squished a little bit at its poles. As you shift, the ring starts to look brighter on one side. That side contains most of the planet's surface information, hidden for now. The further you go, the further the ring separates until you have 2 split bright arcs. Eventually, you end up with a grid that looks like this. Every point has an image of the gravitational lens. So where's the planet? And here's where it becomes like magic. General relativity gives us something called a point spread function, and it tells us exactly how the planet's image gets distorted into that ring. If we just run that process in reverse, we can track where most of the photons in the Einstein ring came from on the planet's surface. And we don't just use one grid. These telescopes just keep working through it for years. The further they get from the sun, the cleaner the images become. And eventually we have millions of Einstein rings to combine into the final image. By imaging the planet over and over again for months, we can slowly remove noise from cloud cover. Imagine spending 20 years and billions of dollars to get this image, and it's cloudy. This also means we get to watch as the planet rotates, mapping all sides of the world as it sweeps along our gravitational lens. If the star system that you're imaging is like TRAPPIST-1 and there are multiple planets you want to target, you simply just locate the imaging cylinder that corresponds to each planet and scan them all individually. After decades of getting these telescopes into place, months of collecting images, analyzing them, and mapping the planet's surface, what you're left with is the single most extraordinary image ever taken by humanity: an alien world in high resolution. For Proxima Centauri b, located 4.2 light-years away from the Earth, each pixel in our image is equal to 1 kilometer on the planet's surface. We would see vast continents with intricate details, oceans and even large lakes, polar ice caps and glaciers. We would see deserts and jungles, forests and grasslands, extreme mountain ranges. We could even spot hurricanes in their weather systems. And most excitingly, if there is an alien civilization on the planet, we might just be able to see their cities. Evidence that we aren't alone in the universe.
Remember yourself being 6 years old. So you're going on under the starry night, and you see those stars, and the question, is there anybody out there?
And don't forget, because we will launch a swarm along multiple different focal lines, we won't just get one planet. Every additional focal line that we add to this mission gives us at least one entire new world to study. If we pick a system like TRAPPIST-1, we actually get 3 different planets using that one focal line. And we aren't just taking pretty images. With this data, we can measure what their atmosphere is made of, look for signs of alien life, and even better, we can directly measure where on the planet those gases are coming from. If there's a lot of methane on the planet, a gas that is typically produced by life here on Earth, we could locate the exact continent or forest that it's coming from. Then, by taking observations over many years, we will get to track things like weather patterns and if the planet is geologically active, if it has tectonic plates and volcanoes like the Earth. If we pull this off, using the sun to image an alien exoplanet, I think it will be the single greatest achievement our species has ever made. Greater than landing on the moon, splitting the atom, sequencing the human genome. So where are we at now? I want this to happen in my lifetime. NASA has something called their Innovative Advanced Concepts Program. They fund high-risk, high-reward ideas. Slava's team completed phase 1 in 2017, showing that a 1-meter telescope at 550 AU can theoretically image exoplanets. The laws of physics allow it. And then in 2018, they completed phase 2. They received $500,000 and made 3 breakthroughs. They figured out how to get the image out of the Einstein ring, developed the swarm architecture that I've shown you, and figured out how to get there quick enough with solar sails. Finally, in 2020, they received phase 3 funding, the final stage of the program. So far, only 3 concepts have ever made it to phase 3. They received $2 million and did a full mission architecture, running the numbers and simulations to say, if you give us this, we will give you the image. Slava has since secured private funding from an undisclosed philanthropic foundation to build a demonstration spacecraft called the Sundiver. It will test the solar sail technology. They aim to launch next year. As a rough estimate, the full SGLT mission all in would cost about $40 billion over 4 decades, about $1 billion a year. Okay, and before you freak out, that's 5 times less than the ISS, 20 times less than the Apollo missions, and don't forget, the US military spends about $2.6 billion every single day. They could fully fund this mission to take a real image of an alien exoplanet in about 2 weeks. And a mission on this scale won't just be NASA. This will be a multi-country global effort to achieve something that Einstein thought would never be possible. This isn't just a fun thought experiment. This is real physics happening today, and I'll make a prediction now. I will see this image of an alien exoplanet, probably Proxima Centauri b, before I turn 70. I'm 25 years old now, so I'm giving them about 50 years. And that will be a beautiful day. But we're not done, because this idea goes way beyond just trying to take a single image. Okay, so imagine we do it. We take this picture of the exoplanet and we see some strong evidence of intelligent alien life. What happens next? The beauty of this idea is it works in both directions, and we can use it to build something extraordinary. the Galactic Internet. Every star in the galaxy can be used in this same way as a gravitational lens. For smaller stars, the focal region starts closer in, and larger stars have it farther out. The focal region for a typical red dwarf star, which makes up about 70% of all of the stars in the galaxy, starts at about 250 AU. That's twice as close as ours. So what if instead of putting a telescope at the focal point, we just put a receiver? Let's understand it with a thought experiment. Imagine we put this receiver at the gravitational focus of the Sun, and our alien neighbors put one at the gravitational focus of Alpha Centauri. The Sun amplifies the signals that they send to us, and Alpha Centauri amplifies any signals that we choose to send to them. The gravitational lenses then boost any signal by a factor of 1 billion. So you can send an extremely weak signal and it arrives crystal clear, with no errors and no loss of quality. When we do the numbers, the signal strength needed for this error-free data link between the Sun and Alpha Centauri works out to be just 0.0001 watts. Your phone's transmitter uses about 2,000 times more energy than that. And we don't have to send radio waves. We can use light, that's optical data transfer, to encode way more information in our messages. All said and done, aliens at Alpha Centauri could receive 10 megabytes of data per second from us. That's enough to stream this video in HD with no buffering. To achieve this without the gravitational lensing, you would need to replace your little 1-meter dish with a telescope 50 kilometers wide and your microwatt signal with the entire electrical output of a small town. The Sun hands you both of these upgrades completely for free. Imagine a future where all of the star systems in the galaxy are connected through gravitationally lensed signals. You can send a message from one side of the galaxy to the other with no data loss at the speed of light for nearly no energy at all. The Galactic Internet. The craziest part is, it might already be on and we just haven't been out there to listen for it. There's a world in which we get our telescopes out to that focal region and realize we aren't the only ones out there, that aliens have been using gravitationally lensed communication this whole time and we just haven't been listening. When I was researching for this video, I couldn't help myself from thinking, what if we push this idea to the extreme? So what's bigger than a star? A black hole. And not just any black hole. What if we use Sagittarius A star, the supermassive black hole at the heart of our very own galaxy? Sag A star has the mass of about 4 million suns, and lensing amplification scales linearly. That's 4 million times more powerful as a lens. But it gets better because most of the problems that we have with SGLT come from the Sun being a hot, bright, angry star. The supermassive black hole has no surface, no corona, and no glaring light. This also means there's no minimum focal distance that we have to go out to. With the Sun, we have to go out to 550 AU because the Sun's physical body blocks the light that could otherwise just pass close to the gravitational center. Light passing the supermassive black hole can skim right past the photon sphere and be deflected at extreme angles, sometimes even orbiting the black hole itself. So what would we see? Imagine we park a telescope 1 light year from the black hole and aim it at a planet on the other side of the galaxy, 100,000 light years away. We would be able to make out individual buildings on its surface. So let's go further. What if we aimed it at a planet in the Andromeda galaxy, 2.5 million light years away? We could still see it at about a 1 kilometer resolution. That's better than what SGLT would give us for Proxima Centauri b, just 4 light years away. A planet millions of light years away, imaged more clearly than our nearest neighbor. And we could even use the gravitational lens around Sag A star to look at a planet in the Virgo cluster, 54 million light years away, and still see continents, oceans, and maybe even cities. Let that sink in. The universe has built us a telescope in the heart of our galaxy that we could use to see planets clearly millions of light years away. But the sad part is, even if we could travel at 99.9999% the speed of light, it would still take 26,000 years to get a telescope in place around Sag A star. The engineering problems for that are well beyond anything we could even consider solving. So at least for now, this is just a fun thought experiment. Okay, my question for you is, once they do this and they release the image, if there were signs of alien life, what does that do to humanity? How would that make you feel?
In the universe, we're definitely not alone. And finding this next exoplanets nearby will help us to appreciate that, look, there is ecosystem.
And let's hope they do it in our lifetime.